Every year, the world produces over 1,800,000,000 tons of steel, but only a tiny fraction of it becomes structures that change the planet's skyline. Picture a sphere 516 feet in diameter, almost like 2 football fields rolled into a ball. 28,000 tons of steel, 13,000 tons, just the outer web that holds the world's largest LED screen. Not a single identical beam, not a single margin for error. Why didn't this project use a single erection cone, a tool that every major construction site relies on? What's the secret to precision that works in the desert under 110-degree heat? Stick around till the end. You'll discover an engineering secret usually only seen inside factories. Let's talk about scale. The total weight of steel in the MSG Sphere structure is 28,000 tons. That's like 2 aircraft carriers. But what interests us is a particular element, what engineers call the Diagrid. It's the external lattice that supports over 1 million LED panels, transforming the sphere into the biggest screen on the planet. The Diagrid itself weighs 13,000 tons of steel. Look at this metal spiderweb wrapping around a sphere nearly 2 football fields in diameter. But this isn't just a lattice. It's a complex 3-dimensional puzzle with 368 nodes and thousands of curved beams, each one needing to find its singular place in space. Here, at this factory, they manufactured these components. And when I say manufactured, I don't just mean cut and welded. I'm talking about creating parts with precision you'd normally see in a watch mechanism, but at the scale of a truck. Schuff Steel. This isn't just a factory. This is one of the most experienced steel fabricators in America, ranking #1 on the ENR list as the top steel erector in the United States. The company was founded in 1976, and over the years, they've built some of the country's most complex structures: NFL stadiums, airports, skyscrapers. But the MSG Sphere was a challenge on a completely different level. Why? Because unlike a rectangular building, or even a curved stadium roof, every single piece of this structure was unique. No 2 beams were alike. Each had its own length, its own bend angle, its own exact position in 3-dimensional space. The project began with digital modeling. Architects from Populous and engineers from Severud Associates created a complete 3-dimensional model in programs like Tekla and Revit. Then that data was sent here to Arizona, where engineers at Schuff Steel broke down the digital model into individual components for fabrication. Now here's where it gets wild. Imagine you're building a sphere 516 feet in diameter. That's the height of a 33-story building in the shape of a ball. Now imagine every single piece of that ball is manufactured at different times, by different people, then trucked 1,000 miles and hoisted by cranes hundreds of feet in the air. And it all has to fit together perfectly. By the time you reach the top of the sphere, your structure could be feet away from where it needs to be. That's why precision was critical. The engineers working on this project used laser scanning and thermal modeling. Why thermal? Because steel expands and contracts with temperature. When you weld a massive beam in the shop at 80 degrees, then haul it out to Nevada, where it might be 110 or 40 degrees, the metal changes size. The team accounted for this. They modeled how each piece would behave at different temperatures, and even scheduled the crane lifts for 2 nights when the steel contracted in the cool air, minimizing dimensional discrepancies. The result? Across the entire project, which included over 7,700 precisely placed brackets, they didn't use a single drift pin. Not one. For those who don't know, that's a special tool you use when holes don't line up, and you need to force parts into alignment and widen the holes to fit the bolts. It's standard practice on most construction sites, but here they didn't need it. Every hole lined up perfectly on the first try. Subscribe to the channel, and let's continue. The foundation of the Diagrid is hollow structural steel sections, HSS, ranging from 12¼ to 24 inches in diameter. These aren't straight pipes. Many of them had to be curved to follow the shape of the sphere. And not just curved, each beam had its own unique radius of curvature. At the factory here, they used specialized equipment for bending pipes of this diameter. It's not a fast process. Each beam is calculated, loaded into a bending press, and slowly, in a controlled manner, formed into the required arc. Then, inspection. Laser scanning confirms that the curvature matches the digital model to within a fraction of an inch. But the beams are only half the story. The real engineering marvel is the nodes. 368 custom steel nodes, each weighing between 3,150 and 14,350 pounds. That's almost like a small car, a node that weighs 7 tons. These nodes were manufactured by Cast Connex using steel casting. Why casting instead of welding? Precision. When you weld a complex node from multiple plates, the heat from welding warps the metal. Even the best welders can't fully control this distortion. And in a structure like this, where 6 or more beams converge at a single point from different angles, even a millimeter of deviation is critical. The cast nodes were custom made in 21 unique designs. After casting, each node underwent CNC machining. Computerized mills worked the connection surfaces with micron-level precision. Each beam pad had an exact angle, calculated to fractions of a degree. Total weight of all the nodes? 1,459 tons of cast and machined steel. Now picture the delivery moment. Massive trailers hauling steel components from Phoenix to Las Vegas. Some beams over 50 feet long. Nodes loaded onto specialized flatbeds. This isn't your typical delivery. Every piece has its number, its purpose, its exact place in the puzzle. On the Las Vegas construction site, they installed one of the biggest cranes ever used in the city. Just getting it there took 120 trucks. They needed a separate crane just to assemble the main crane, a process that took 18 days. And then assembly began. The first Diagrid section rose into the air. Massive steel triangles against the desert sky, a futuristic skeleton gradually taking shape. The structure grew in rings, each horizontal circle at a given latitude, creating a stable foundation for the next level. By March 2020, construction reached its widest point, 516 feet in diameter at 108 feet above the ground. This was a critical moment. Now the structure had to start tapering towards the top, creating the upper half of the sphere. But the Diagrid, this is load-bearing structure, supporting colossal weight. Over 400 LED megapanels, each containing thousands of individual LED pucks. Total external screen area, 580,000 square feet. The largest LED screen on the planet. Each megapanel attaches to the Diagrid through precisely positioned brackets. Remember those 7,700 brackets I mentioned? Each one installed with millimeter precision, because the LED panels have to be aligned perfectly to create a seamless image across such a massive area. And this metal mesh had to withstand more than just weight. Wind loads in the desert can be extreme. Thermal expansion from the sun heating one side of the sphere more than the other. Dynamic loads from concerts inside, where 18,000 people move to the beat of the music. Engineers modeled all these scenarios. Every node, every beam was calculated not just to handle static weight, but to work as a single flexible system that distributes loads and absorbs shocks. Every year, thousands of skyscrapers go up worldwide, consuming millions of tons of steel. But what actually keeps a 1,550-foot tower thinner than a pencil standing? Picture a 120-story building with a base just 82 feet wide, a 1:19 ratio. Logic says it should fall. The secret isn't in the glass or the concrete. Just 484 bolts, each costing as much as a car, hold 50,000 tons of weight. How does a small factory in Philadelphia make parts that withstand hurricanes and million-pound loads? And why could one mistake change Manhattan's skyline forever? Stick around, you'll learn what even engineers won't tell you. When I pulled up to the Hayden Bolts factory in Philadelphia's industrial district, I thought I had the wrong place. Small building, regular parking lot, nothing grand. I walked inside, and the first thing that hit me, the smell. Hot oil, superheated metal, ozone from welding. The shop floor held steady at 95 degrees Fahrenheit, even in winter. Workers in safety goggles and heavy gloves moved between machines, each one the size of my garage. Jim met me, the plant's chief engineer. Guy in his mid-50s, voice trained to cut through the roar of a press. "You here to see how we make the bolts for Central Park Tower?" he asked. I nodded. Central Park Tower, a 120-story skyscraper rising 1,550 feet. Tallest residential building in the world. But here's the crazy part. It's narrow. Base is only 82 feet wide. Height to width ratio, 1:19. It's like standing a pencil on end. Any breeze should knock it over. "Why doesn't it fall?" I asked. Jim smiled. "Because of the 484 bolts we're making right now. Each one goes 12 feet deep into the concrete foundation and holds the building's steel frame." He led me to a rack where steel rods lay. "This is where it starts," he said, pointing to a rod 4 inches in diameter and 10 feet long. "This is ASTMA 354 grade BD steel. Tensile strength, 200,000 pounds per square inch. For comparison, regular structural steel has 50,000. I picked up the rod, just to try. It weighed 145 pounds. Stage 1. Heating. The rod gets placed in an induction furnace, where it heats up to 1900 degrees Fahrenheit. At that temperature, the steel glows bright orange, almost white. When the rod reaches the right temperature, a robotic arm pulls it out and transfers it to the forging press. This press is a 50-ton monster capable of generating 1,500 tons of force. One end of the rod gets clamped into a die, and the press strikes it 4 times. Under the press strikes, the metal deforms, forming the hexagonal head of the bolt. Each strike, 250 tons of force. The steel flows into the mold, metal fibers compress, the structure becomes stronger. In 15 seconds, a shapeless rod transforms into a bolt with a head 6 inches across. I see lines running along the metal, like rivers on a map. When you strike metal properly in the right place, the fibers don't tear. They bend, they flow around the shape. That makes the head incredibly strong. Next stage, normalization. The hot bolt cools freely in a special chamber for 8 hours. If you cool it fast, internal stress builds up in the metal, and the bolt could crack under load years down the line. Slow cooling allows stable relaxation. The fibers align themselves in the optimal configuration. Then comes the most interesting part, thread rolling. We walked up to a massive machine that looked like an industrial press. "This is our main weapon," Jim said proudly. Thread rolling machine made by Feta, Germany. Costs $1,002,000. He showed me 2 steel rollers, 18 inches in diameter each. Carved into the roller surfaces were perfect grooves, the negative of the future threads. The bolt gets placed between 2 rollers. They start spinning toward each other at 50 revolutions per minute, creating 50 tons of pressure. Under that pressure, the rollers press into the bolt's surface, deforming the metal and forming the threads. "Why is this better than cutting?" I asked. Jim grabbed 2 bolts, one with rolled threads, the other cut. When you cut threads with a tool, you're slicing through the metal fibers. Look at this cut bolt under a microscope. The fibers are severed. Those are weak points. He pointed to the rolled thread bolt. But here, the fibers don't break. They bend. They follow the thread profile. The metal structure stays intact. Strength increases by 35%, and fatigue strength, the ability to withstand cyclic loads, by 60%. I ran my finger along the threads of the rolled bolt. They were perfectly smooth, without any burrs or irregularities. When the bolts tightened, the threads dig into the nuts so hard that loosening is basically impossible. This is critical for skyscrapers. They're constantly getting hammered by wind. Next stage, heat treatment. Bolts go into a furnace and get heated to 1550 degrees Fahrenheit, then rapidly cooled in an oil bath. This is called quenching. The steel becomes exceptionally hard, but brittle. So right after quenching comes tempering. The bolts get heated again, but this time to 600 degrees and fully cooled. This removes the brittleness while keeping the hardness. The result? Perfect balance. The bolt's hard on the outside, but tough enough inside that it won't crack under impact loading. Now for the moment of truth, Jim said, leading me into the lab. A finished bolt sat mounted on a test stand. Every fifth bolt goes through destructive testing. We take one from the batch and pull it until it breaks. The testing machine, a hydraulic press capable of generating 2 million pounds of force. The bolt gets clamped at both ends, and the press starts pulling. Numbers race across the screen. 100,000 pounds. 200,000. 300. Spec requires the bolt to withstand 1,200,000 pounds, Jim explains. The numbers climb. 800, 900, 1 million, 1 million, 200,000. Passed, the lab tech calls out, but the press keeps pulling. 1,400,000, 500, 600. Suddenly, a sharp crack. The bolt failed at 1,700,000 pounds. 42% safety margin, Jim says, satisfied. That's exactly what we need. He showed me the destroyed bolt. The failure didn't happen at the threads. Those are intact. The break is in the bolt's body, and the metal stretched before it snapped. This is ductile failure, he explains. The bolt deforms first, warning you about overload, then it breaks. That gives you time to realize something's wrong. We got back to the shop floor, where a finished batch of bolts for Central Park Tower was already laid out. 484 pieces, each 9 feet long, 130 pounds in weight. They were identical. The difference in length didn't exceed a 1/16 of an inch. How much does one of these bolts cost? I asked. Jim thought for a moment. Factoring in material, machining, testing, certification, $32,000. Yeah, that's the price of a budget car. When you're building a 100-story tower that weighs 50,000 tons and sits on a footprint smaller than a basketball court, every single part has to be perfect. Jim tells me about a recent story. In 2012, Hurricane Sandy hit New York. Winds 105 miles per hour. I was standing here thinking about our bolts in 157, the tallest residential skyscraper at the time. 105 miles per hour. That's 8,000 pounds of force per square foot of facade. The building swayed 3 feet from center. 3 feet! Every year, the world produces over 1,800,000,000 tons of steel. That's enough to build thousands of bridges, but only one of them will become North America's longest cable-stayed bridge, the Gordie Howe International Bridge. 125,000 tons of metal, over 1 million bolts, and a span of nearly 3,000 feet with not a single support in the water. How do two countries stitch steel together over a river? And what happens if even 1 millimeter goes wrong? Stick around to the end, and you'll see the moment when American and Canadian metal literally kiss in the sky. The birth of the steel backbone for the Gordie Howe Bridge starts long before the first beam reaches the construction site. This is a cross-border industrial operation where the Canam Group plays the starring role. The steel for this project isn't just metal. It's the result of collaboration between American and Canadian steel giants. Sheets of high-strength specialty steel are forged at mills in both countries. Then massive rail cars funnel them towards specialized fabrication shops. When you walk into a Canam plant, the first thing that hits you is how modern robotics tames raw matter. You won't see blacksmiths with hammers here. Laser systems and giant computer-controlled machines rule this space. Steel plates several inches thick are cut by laser or plasma with precision down to tenths of an inch. That's critical because each edge girder is made up of dozens of elements that must fit together perfectly during welding. The most dramatic moment at the plant? Assembling that famous box girder beam. Massive magnetic cranes hoist steel plates 49 feet long and position them into specialized assembly jigs. Here begins a process engineers call submerged arc welding. It's an automated technique where the welding head travels along the seam, hidden beneath a layer of special powder, flux. This prevents metal spatter and ensures perfect joint quality. Inside, the beam is reinforced with countless stiffener ribs. These are vertical steel partitions that prevent the structure from deforming under the colossal weight of the roadway. Every weld passes through the hands of inspectors armed with ultrasonic and X-ray flaw detectors. On the Gordie Howe Bridge, there's no room for average quality. If they find even a microscopic air bubble inside the metal, the part gets rejected. After welding, the finished beam heads to the shot blasting chamber, where its surface gets cleaned to a shine, then receives multiple layers of special polymer coating. This is armor against moisture and salt, designed to protect the steel for 100 years. Folks, check this out. I'm standing at a safe distance right now, but even from here, this thing looks completely unreal. We're used to the word beam, but on the Gordie Howe International Bridge project, that term takes on a whole new meaning. Each of these edge girders is a 100-ton steel titan that's literally twice my height. I've watched them get moved. It's a full-on special operation. Giant multi-axle platforms creep slowly across the construction site, and the gravel literally buckles beneath them. When they lift one of these beams into the air, it blocks out the sky. That's the moment you realize there's nothing impossible in this world for someone who's learned to tame steel at this scale. This is pure, raw, 100-ton power that's about to become part of the longest cable-stayed bridge in North America. Ever build with Legos as a kid? Now imagine one piece weighs 100 tons, and instead of plastic connectors, you've got a blazing welding arc. We're on the banks of the Detroit River, and what you see behind me, engineers call an assembly node, but I'm calling it a playground for giants. The assembly process for the Gordie Howe International Bridge means building giant modules right here, on the ground. You can't just hoist one beam and clip it together in the sky. First, on special steel jigs along the shore, these 100-ton edge girders get welded into single sections. It looks incredible. 2 parallel edge beams connected by cross-steel trusses, forming a massive frame. When a section's complete, it resembles part of an aircraft carrier deck that someone decided to build in the middle of an industrial zone. Why do they do this on shore? Because here, welders have something they don't have at 492 feet up: stability. Every seam, every joint has to be perfect. I walked up to these guys. They're working in special masks with fresh air supply, because the welding intensity here is so high that the air around them literally burns up. You see these welds? They're as wide as my palm. Robotic welders pass dozens of times over the exact same spot, laying down layer after layer to create a monolithic joint that no storm will ever tear apart. Now look at these bolted connections. Where welding can't be used, thousands of high-strength bolts take over. Each one is tightened with such force that the steel plates start working as a single unit through friction force. When a section like this is fully assembled, they check it with laser scanners. Accuracy has to be within an inch. If there's even a hair's width of misalignment, literally the thickness of a matchstick, then midway across the river, when the Canadian side meets the American side, they just won't line up. The feeling of being next to one of these sections? Pure adrenaline. You're standing inside a steel box that's about to hang over a gorge, carrying thousands of people. The sound here is something else. Constant grinding of metal, hissing of pneumatic tools, and the rumble of heavy cranes. Across the water, slow and almost silent, a massive barge glides forward. Resting on its deck is the very section we saw on shore. A steel frame with edge girders weighing hundreds of tons. From the bank, it looks like a surreal steel island drifting between two countries. But the moment that barge locks into position directly beneath the bridge span, the air gets electric. You look up, and 150 feet above the water, you see the red jaws, special lifting devices mounted on the edges of the completed spans. What engineers call the heavy lift is beginning. This isn't a quick process. When the winches start working, the steel cables tighten like strings on a giant guitar. You hear that sound? That low, guttural groan of metal accepting colossal weight. The section slowly lifts off the barge. The first few feet of empty space appear between the water and the steel bus. In that moment, all the weight of this monster bears down on the pylons and cables. You literally see the bridge settle a few inches, coming alive under the load. I stood on the shore, holding my breath. Surveyors with laser rangefinders track every millimeter of lift, second by second. And then, when the section finally lines up with the bridge edge, the most critical part begins. The ironworkers, who look like tiny dots against the white beams, start catching the section. They use hydraulic jacks to perfectly align the bolt holes. This is the moment when American and Canadian steel has to kiss. When the first pin slides through both plates, a wave of relief you can physically feel washes over the construction site. Its main span is 2,799 feet. That's a massive pile of steel hanging over water with zero support in the river. That makes it the longest cable-stayed bridge in all of North America. Over 125,000 tons of structural steel went into this thing. Constant corrosion from salt water. There's colossal enough metal here to build 1.5 Kitty Hawk-class aircraft carriers. And what about the fasteners? Connecting all these massive beams took over 1 million high-strength bolts. Each bolt is a tiny guarantee that this backbone will handle 100 years of use and more than 2.5 million trucks every single year. It's a genuine metal ocean, tamed by human ingenuity. Did you enjoy this journey from cutting up aircraft carriers in Texas to the birth of new titans in Detroit? If so, you know what to do. Hit that steel bell, smash the like button, and make sure to subscribe to the channel. There's a metal so rare that humanity mines less of it in an entire year than gold in a single day. A metal that costs $2,000 to $4,000 per pound. A metal you've never heard of, but one that's keeping the plane you flew on for vacation from falling out of the sky right now. This is rhenium, the rarest stable element in Earth's crust. A silvery white metal that doesn't exist as its own ore and is only extracted as a byproduct. Without it, we wouldn't have modern jet engines, and aviation would be stuck at mid-last century levels. Let's dive into the world of the planet's most exclusive mineral, where every gram is worth its weight in gold, and applications are measured not in tons, but in pounds. Let's start with the scale of rarity. Rhenium makes up about 7 ten-thousandths of a part per million in Earth's crust. For comparison, gold is 4 ten-thousandths, platinum is 5 ten-thousandths. But gold and platinum can be found as nuggets or concentrated ores. Rhenium never happens that way. It's scattered as microscopic impurities in other ores, mostly molybdenum and copper. The concentration is so low that even talking about rhenium ore isn't really accurate. It's always ore of something else that just happens to contain rhenium. Rhenium itself looks like a silvery white metal with a slight grayish tint. But most people have never seen pure rhenium. Even in industry, it's often used as alloys or powder. In nature, rhenium occurs in only one mineral, jacasganite, which is so rare it exists in literally just a few places on the planet and has no commercial value. All industrial rhenium is obtained as a byproduct of processing molybdenum concentrates, which themselves are a byproduct of copper mining. It's a byproduct of a byproduct. Imagine the scale. To get 1 kilogram of rhenium, you need to process about 200,000 tons of copper ore. 200,000 tons of rock for a kilogram of metal. It's like looking for a needle, not in a haystack, but in a field planted with hay. The main sources of rhenium are molybdenum mines in Chile, the USA, Kazakhstan, and Armenia. Chile dominates, about 50% of global production. The Chuquicamata mine in the Atacama Desert is one of the largest open-pit mines on the planet, where copper and molybdenum are extracted, with rhenium obtained as a side benefit. The pit is so massive it's visible from space, about 2.8 miles long, 1.9 miles wide, and over half a mile deep. The rhenium extraction process is complex and multi-staged. First, they mine copper ore and concentrate it through flotation, producing copper concentrate. This concentrate contains molybdenum, which is also concentrated and separated. Molybdenum concentrate is molybdenum sulfide with microscopic traces of rhenium, typically from 0.05 to 0.2%. Still with me? Let's keep going. The molybdenum concentrate gets roasted in special furnaces at temperatures around 2000 degrees Fahrenheit or higher in air. Molybdenum oxidizes to molybdenum trioxide, which can then be reduced to metal. But rhenium behaves differently. It oxidizes to rhenium heptoxide, which at this temperature evaporates and escapes with the gases. The gases pass through a complex system of scrubbers, towers where the gases are washed with water or alkaline solutions. Rhenium heptoxide dissolves, forming rhenic acid or perinates. The concentration of rhenium in these solutions is minuscule, grams per ounce, but it's something workable. The solution is purified from impurities of molybdenum, copper, lead, and other metals through multi-stage chemical treatment. Then, rhenium is precipitated as a white crystalline powder. This is the most common form of rhenium feedstock for further processing. To obtain metallic rhenium, the powder is heated in a stream of hydrogen. Hydrogen reduces the rhenium oxide to metal. The result is rhenium powder, which can then be sintered, melted, or used directly. Every year, humanity produces around 50 tons of rhenium. 50 tons! For comparison, we mine roughly 3,000 tons of gold annually and 20 million tons of copper. Rhenium is so rare that global stockpiles at any given moment are measured in hundreds of tons, not thousands or millions. So here's the question: why bother mining something this scarce? The answer: jet engines. Close to 80% of all rhenium goes into the aviation industry to manufacture superalloys used for making turbine blades. A jet engine turbine blade operates in absolute hell. Gas temperatures hit 3,000 degrees. Pressure is massive. The blade spins at tens of thousands of revolutions per minute, experiencing loads of hundreds of tons per square inch. Corrosive environment with sulfur impurities from aviation fuel. And all of this for years of continuous operation with zero margin for error. If a blade cracks mid-flight, the engine disintegrates, the plane goes down. Nickel superalloys, the primary material for turbine blades, contain nickel, chromium, cobalt, tungsten, molybdenum, aluminum, and titanium. But even these complex alloys couldn't withstand temperatures over several thousand degrees for extended periods. Until they added rhenium. Rhenium does something remarkable. It dissolves into the nickel matrix of the superalloy and prevents defects from moving through the crystal structure at high temperatures. This is called creep, the gradual deformation of metal under load at temperature. All metals creep, but rhenium slows this process down by several times. Adding just 3% rhenium to a nickel superalloy increases the operating temperature by about 54 degrees Fahrenheit. Doesn't sound like much, but in jet engines, every 18 degrees of additional temperature gives roughly 1% increase in efficiency. And efficiency means fuel consumption, flight range, airline economics. Modern superalloys contain up to 6% rhenium. These are the so-called second and third generation superalloys. A single turbine blade can contain 5 to 20 grams of rhenium. One Boeing 787 or Airbus A350 engine contains roughly 13 pounds of rhenium in its blades. 13 pounds of metal worth $30,000 to $60,000 in a single engine. And a plane has 2 engines. Thousands of jet engines are manufactured every year: passenger, cargo, military. Nearly all the rhenium mined in the world goes right there. Because of its rarity and high price, the industry is desperately trying to cut rhenium consumption. New generations of superalloys are being developed with lower content or using ruthenium, an element from the same group that could theoretically replace rhenium. But ruthenium is even rarer and more expensive. So for now, it's just research. Single crystal blade technology lets manufacturers use rhenium more efficiently. Instead of a polycrystalline structure, the blade is grown as one massive crystal with no grain boundaries, the weak spots. This allows them to reduce rhenium content while maintaining performance. But the process is complex and expensive. Each blade is grown individually in specialized furnaces with extremely slow, controlled cooling. Recycling rhenium from spent blades is critically important. After thousands of hours of operation, blades wear out and get replaced. Old blades aren't thrown away. They're melted down. Rhenium and other valuable metals are extracted and used again. About 30% of rhenium comes from secondary recycling. That's more than most other metals simply because of its enormous value. The remaining 20% of rhenium goes into other applications. Catalysts in petroleum refining, platinum-rhenium catalysts for reforming boost gasoline octane ratings, filaments for mass spectrometers and electron microscopes, anode materials for X-ray tubes. Rhenium's strategic importance is massive. Countries without access to rhenium can't manufacture modern jet engines. This isn't just about civilian aviation, it's military too. Fighters, bombers, cruise missiles. The US, with its own molybdenum mines, secures its rhenium supply. Europe and Asia depend on imports, mostly from Chile and the US. China is aggressively ramping up rhenium production, developing their own molybdenum deposits. They get it. Without rhenium, you can't build a competitive aviation industry. Here's the thing. Rhenium was one of the last stable elements ever discovered. German chemists found it back in 1925 while analyzing platinum ore with spectral analysis. They named it after the Rhine, Rhenus in Latin. Before that, Mendeleev had predicted element number 75 would exist, but nobody could find it. It was just too incredibly rare. In a world where most materials lose their shape and strength under the crushing force of extreme heat, there exists a special stone whose internal structure is hardened to withstand truly hellish temperatures. Molybdenum ore, often found as unassuming gray-blue crystals or embedded in granite massifs, is the source of one of the most refractory metals on the planet. When ordinary iron becomes soft as wax and aluminum turns into a puddle of weak metal, molybdenum maintains its unwavering hardness. This makes it not just a valuable industrial resource, but a strategic component without which the development of aviation, space exploration, and the creation of the most powerful weapon systems is impossible. This metal's journey begins deep in the Earth's crust, where millions of years ago, under colossal pressure, the mineral molybdenite was formed. Molybdenite looks a lot like graphite on the outside. It feels just as greasy to the touch, leaves a mark on paper, and has that distinctive metallic shine. For centuries, people confused it with lead, until 18th century chemists proved that this heavy gray mineral was hiding something new, an element with unique properties. Molybdenum's maximum melting point exceeds 4,700 degrees Fahrenheit. That puts it right up there with heat resistance giants like tungsten and tantalum. But here's the thing. Unlike them, molybdenum is significantly lighter, which makes it the perfect candidate for applications where weight is critical. Mining molybdenum ore is a complex engineering challenge because the concentration of metal in the rock is extremely low. Molybdenum is often just a byproduct when mining copper deposits, but its value runs so high that even tiny percentages make extraction profitable. The process of getting metal from rock starts with massive blasting operations in open pits or deep mines. Huge volumes of ore get crushed into fine sand, which then heads to flotation plants. There, in a water environment with special reagents added, molybdenite particles attach to air bubbles and rise to the surface, forming a concentrate. This gray mass later goes through a roasting stage at high temperatures, where the sulfur burns off, leaving molybdenum oxide. This powder becomes the foundation for producing ferromolybdenum, an iron alloy that's the main component in the metallurgical industry. Every single ton of this concentrate comes from processing thousands of tons of rock. That's how energy intensive and massive this operation really is. Most of the molybdenum mined worldwide goes into creating high-performance alloys. Add even a tiny amount of this element, and it radically transforms the metal's properties. Molybdenum acts like a reinforcement for the crystal lattice, preventing the metal from deforming under extreme heat. This phenomenon allows us to create steels that don't become brittle or flow under load. That's why molybdenum alloys have become indispensable in building gas turbines and jet engines. Inside a combustion chamber, temperatures reach levels that would instantly destroy ordinary structural materials. But molybdenum lets turbine blades operate at the very edge of what's physically possible, delivering massive thrust and rock-solid flight reliability. The weapons sector is another area where molybdenum ore successfully plays a role. The history of using this metal in military affairs began during World War I, when German industry used molybdenum steel to create super-heavy artillery. It turned out that barrels made from this steel could withstand significantly more shots and didn't deform from overheating as quickly as others. Today, molybdenum is a mandatory element in tank armor and armor-piercing shells. Its ability to combine hardness with toughness makes armor plates capable of absorbing impact energy without shattering into fragments. In rocket technology, molybdenum is the choice for manufacturing nozzles and casing elements that come into contact with superheated gases during launch and flight through dense atmospheric layers. Molybdenum alloys show incredible resistance to aggressive chemical environments. That opens doors to petrochemical plants and nuclear power. Pipelines pumping corrosive substances under high pressure, reactors where complex chemical transformations happen. This metal's everywhere, keeping systems running strong for decades. In nuclear reactors, molybdenum's used because it maintains structural stability under constant neutron bombardment, a critical safety factor. This metal fears neither fire, nor acid, nor radiation, making it a true universal tool in the hands of modern engineers. The global molybdenum ore market, highly concentrated. Just a handful of regions control production. China, the US, and Chile are the main suppliers of this resource, and any disruption in their output instantly impacts the cost of high-tech products worldwide. Molybdenum's strategic importance forces major powers to stockpile significant reserves of this metal in case of geopolitical crisis. Exploration for new deposits never stops, because demand for energy-efficient and heat-resistant materials only keeps growing. Take renewable energy development, for instance. It requires molybdenum for next-generation solar panels and wind turbine components that need to survive brutal offshore conditions. The environmental side of molybdenum, or mining and processing, demands serious attention. With extraction involving the movement of massive amounts of earth, companies are forced to implement complex monitoring and reclamation systems. Waste rock dumps and tailings ponds must be reliably sealed to prevent heavy metals from leaching into groundwater. At the same time, molybdenum is highly recyclable. Scrap high-grade steels, spent turbines, and parts from dismantled equipment remain a valuable source of secondary metal, allowing us to reduce the burden on natural ecosystems. A circular economy in this industry isn't just about environmental concerns, it's a path toward lowering production costs down the road. It's fascinating to watch how the journey of metal mirrors the progress of human thought. What was once dismissed as useless soft rock is now the heart of our most sophisticated machines. The transformation of molybdenum into an aircraft engine component. That's a chain of technological victories. Processing through every stage, from that first blast in the quarry to the final polishing of the alloy, demands precision and deep understanding of materials physics. Molybdenum doesn't forgive mistakes. Working with it requires specialized tooling and particular cooling regimes, but the payoff justifies every ounce of effort. This metal is for those situations where reliability is a synonym for survival. The scale of molybdenum use? It's an indicator of a nation's industrial muscle. A country capable of producing and processing these complex alloys automatically enters the upper league of technological players. This drives scientific research in metallurgy, where scientists are pushing to create even more resilient compounds based on molybdenum, adding chromium, nickel, or cobalt into the mix. Molybdenum ore remains one of the resource remnants of our civilization, bridging the planet's geological past and its technological future. It's a symbol of resilience and unwavering strength, a material that lets us operate where scorching gas and destructive chemistry rule. From a humble chunk of molybdenite to a complex turbine blade or armor plate, this metal undergoes a journey of refinement and transformation to become a reliable foundation for human progress. Its story is a tale of how we learned to tame the elements, using gifts from the Earth's depths to create things that seem stronger than nature itself. And as long as humanity keeps searching for ways to work faster, fly higher, and generate more energy, molybdenum will remain that same indispensable element, conquering any inferno in service of our goals. This rock decides whether steel breaks or holds. Without it, there wouldn't be a single bridge, skyscraper, car, or ship. A metal nobody sees, nobody hears about, but it's in every piece of steel around you. Add too little, the steel shatters like glass at the first hit. Add too much, it gets brittle and cracks. But add just the right amount, and steel becomes so tough it can take a sledgehammer blow, deflect a bullet, and let a tank roll over it without a scratch. This is manganese, the most underrated element in metallurgy, a black-gray rock from deposits scattered across the planet, deciding one simple question: will your steel break or not? Let's dive into the world of manganese ore, where chemistry meets mechanics and geology determines whether a building stands or falls. Let's start with the basics. Manganese is a silvery gray metal, brittle in its pure form, that nobody ever uses on its own. Its magic only shows up in steel alloys. Add 0.5% to 1% manganese to ordinary steel, and it suddenly becomes stronger, tougher, more impact resistant. Bump the content up to 12 to 14%, you get Hadfield steel, so hard they make excavator teeth, tank treads, safes, and bulletproof plates out of it. 90% of all manganese in the world goes into metallurgy. Without it, modern steel simply wouldn't exist. The rest gets used in batteries, ceramic pigments, fertilizers, and the chemical industry. But the main role? Making steel what we know it to be. Strong, reliable, able to take a beating. Manganese ore looks pretty unimpressive. The most common minerals are pyrolusite, silomelane, and manganite. They range from black to dark gray, sometimes with a metallic sheen. The structure can be crystalline, granular, or earthy. The last one looks like black powder that gets your hands dirty. If you see dark rock that leaves black marks on your fingers, chances are it's manganese ore. Manganese concentration in the ore varies from 20 to 50% manganese oxide. Rich ores with over 45% are considered high grade and can be smelted directly. Poorer ores need to be enriched. The world also has oceanic manganese nodules, potato-like rocks on the ocean floor that contain manganese along with nickel, cobalt, and copper. But commercial mining of these is still in its infancy. The biggest deposits are in South Africa, Australia, Gabon, Brazil, and China. South Africa dominates, about 30% of global production. The Kalahari deposit holds roughly 75% of the world's known manganese reserves. It's a geologic formation 2 billion years old, from when Earth's atmosphere was just getting saturated with oxygen, and manganese was settling en masse on the ancient ocean floor. Mining happens mostly in open pits. Manganese ore typically sits in layers anywhere from a few feet to hundreds of feet down. They strip the deposit, remove the upper layers of waste rock, then drilling rigs bore holes, they load explosives, and detonate. The blasts kick up black dust clouds you can see for miles. Excavators load the blasted ore into dump trucks that haul 200 to 400 tons, hauling it off to the crushers. The ore gets crushed, sorted by size and quality. High-grade ore, straight to the steel mills. Low-grade ore needs enriching, separating manganese minerals from waste rock using gravity methods, magnetic separation, or flotation. Manganese minerals are heavier and have different magnetic properties compared to waste rock, which lets you split them apart. Processing manganese ore at metallurgical plants happens in blast furnaces or electric arc furnaces. For steel production, you don't need pure manganese. They use ferromanganese, an alloy of manganese and iron containing 75 to 80% manganese, or silicomanganese, an alloy with silicon, around 65% manganese. Ore gets loaded into an electric furnace alongside coke and fluxes, then a massive electric current passes through. Inside, temperatures hit 3,000 degrees Fahrenheit. Carbon reduces manganese oxide into metal. Molten ferromanganese sinks to the furnace bottom. Slag floats to the surface. Every few hours they open the tap hole, and a fiery river of metal flows into ladles. One furnace devours megawatts of electricity. That's like a small town. That's why ferromanganese plants get built near cheap power sources, hydroelectric dams, or coal-fired stations. Norway uses cheap hydropower, which is why Norwegian ferromanganese is considered some of the highest quality. Now let's talk about why manganese is so critical for steel. First, it deoxidizes the steel. It binds oxygen, which makes steel brittle and porous. Second, it binds sulfur, which also messes with the properties. Sulfur forms manganese sulfide with manganese, which floats up into the slag and gets removed. Without manganese, sulfur would stay in the steel and cause cracking during hot working. The steel would just fall apart. Third, manganese increases strength and toughness. It dissolves into the steel, changes the crystal structure, prevents grain growth. Fine-grained steel is stronger than coarse-grained steel. Manganese also improves hardenability, the ability of steel to harden deep down when you quench it. This lets you make large parts that harden all the way through, not just on the surface. In structural steels, manganese content typically ranges from 0.3 to 0.8%. These are standard steels for construction, mechanical engineering, automobiles. In high-strength steels, the content can reach 1.5%. These steels are used for critical structures, bridges, ship hulls, oil pipelines, skyscraper frames. Now for the real star, Hadfield steel, also known as austenitic manganese steel. Invented by Englishman Robert Hadfield in 1882, contains 12 to 14% manganese and 1 to 1.4% carbon. This steel has an amazing property. It's relatively soft inside, but during impact or abrasive action, the surface layer instantly hardens, becoming extremely hard. This effect is called work hardening. The harder you hit Hadfield steel, the tougher it gets. That's why it's used for anything that takes extreme impact loads. Tank tracks, excavator teeth and buckets, rock crushers, railroad frogs and crossings, mill liners for grinding ore. Even safes and bulletproof plates were made from this steel. A bullet striking a Hadfield steel plate meets a surface that hardens on impact. The bullet deforms or shatters, while the plate stays nearly undamaged. During World War I, they made helmets and armor plates from it. Now it's used for heavy mining equipment, buckets that load sharp rocks, crushers that pulverize boulders. Hadfield steel gets heated, held at temperature, then quenched rapidly in water. This locks the manganese in solution and creates the structure you want. Every year, the world mines about 20 million tons of manganese ore. From that, roughly 20 million tons of ferromanganese and silicomanganese get produced. Each ton of steel contains 3 to 10 kilograms of manganese, and we make about 2 billion tons of steel per year. Do the math, millions of tons of manganese dissolve into steel every single year, making it strong. Manganese ore prices swing from $5 to $10 per ton, depending on quality. Sounds cheap compared to cobalt or tantalum, but the volumes are massive, so the manganese market is worth billions. Ferromanganese costs around $1,000 to $2,000 per ton. For steel mills, that's serious money, but without manganese, you simply can't make steel. Mining manganese does have environmental consequences. Open pits reshape the landscape, dust pollutes the air, and processing plant tailings contain heavy metals. But compared to cobalt or coltan, the problems are smaller. Extraction is more industrialized and happens in countries with stricter regulations. Oceanic manganese nodules are a potential future source. On the Pacific Ocean floor, at depths of 2.5 to nearly 4 miles, billions of tons of these rocks just sit there. Manganese concentration is around 25%, plus nickel, cobalt, and copper. But deep-sea mining technology is complex, expensive, and carries unknown ecological consequences for ocean ecosystems. The international community remains cautious about issuing permits. Recycling manganese from scrap metal happens automatically. When steel gets remelted, the manganese stays in the alloy. But some gets lost in slag and scale, so constant addition of fresh manganese is needed. The circular cycle is incomplete. Primary extraction remains necessary. Researchers are looking for ways to reduce manganese consumption or find substitutes. But so far, nothing can fully replace it in steel. Other elements, vanadium, molybdenum, chromium, also improve properties, but they don't handle deoxidation and sulfur binding as effectively. Manganese remains irreplaceable. Every year, humanity produces over 4 billion tons of concrete, more than any other material on the planet. It's what our cities, bridges, and roads are built from. But every crack is like a tiny timer ticking toward destruction, started the moment water seeps inside. Now imagine concrete that actually lives, breathes, and heals itself. No people, no repairs. Deep in labs across the Netherlands, USA, and Japan, a game-changing material is being born. Inside it, bacteria or microcapsules that can seal cracks on their own, just like skin healing after a wound. How is this even possible? How did a lifeless material gain the ability to regenerate? Stick around until the end, and you'll find out how scientists brought concrete to life. Self-healing concrete. Sounds like something out of a sci-fi movie, but it's already here. Scientists invented it to solve one of construction's biggest headaches: cracks. Regular concrete starts drying out and cracking over time from temperature swings, moisture, or just plain stress. And a crack isn't just a scratch. Water gets inside, the rebar starts rusting, the structure weakens, and eventually, you're looking at expensive repairs or even a collapse. That's why researchers decided to create concrete that can patch itself up, no human help required. Sounds crazy, but it's actually pretty logical. There are two main technologies that make this possible: microbiological and mineral. The first one uses real living organisms. So-called bioconcrete was developed by Dutch researchers, and the principle is pretty straightforward. They add special bacteria to regular concrete mix, usually Bacillus pseudofermis or Bacillus conii. These bacteria can stay dormant for years, like seeds in dry soil. Along with the bacteria, they add nutrients, usually calcium lactate. And while the concrete stays intact, the bacteria just sleep. But when a crack forms and moisture gets in, they wake up. That's when the real microscopic work begins. The bacteria start consuming the nutrient substrate and, through their life processes, produce calcium carbonate, basically the same mineral that makes up seashells and limestone. That's what seals the crack from the inside, like the concrete is fixing itself. The results are impressive. Micro cracks up to 0.03 of an inch can disappear completely within a few weeks. And all without human intervention, purely thanks to nature that's been built into an artificial material. The second technology is less alive, but no less impressive. Instead of bacteria, it uses chemistry. Tiny capsules are added to the concrete, containing an active substance inside. For example, epoxy resin or sodium silicate. These grain-sized capsules are evenly distributed throughout the mix. When the concrete cracks, some of the capsules burst too. The substance inside comes out, fills the crack, and hardens on contact with air or moisture. The result is the material literally heals itself. It's similar to how certain car paints can heal scratches with heat, Except this process is way more complex and large-scale. The advantage of this approach is that it works even in dry conditions, where bacteria might not activate. The downside is cost. Creating the capsules is more complex, so this concrete is pricier. But when you calculate the cost of repairing bridges or tunnels, it becomes clear. The payoff is huge. Interestingly, these technologies don't cancel each other out. Some companies are experimenting with combining biological and chemical methods to create concrete that could self-heal under any conditions. Underwater, in the desert, or in freezing cold. Testing shows that structures made with this concrete last 2 to 3 times longer than regular ones. Bridges, roads, dams, parking garages, all of this can be made nearly eternal. For example, the Netherlands already built a lakeside lifeguard station using bioconcrete, and after several years, it hasn't needed any repairs. The idea is spreading fast around the world. In the US, these materials are being tested in bridges, in the UK, in sidewalk paving, and in Japan, even in concrete for coastal reinforcements that have to withstand salt water. Regular concrete, even the highest quality, has a shelf life, roughly 50 years. After that, cracks start appearing, water penetrates inside, rebar rusts, and the structure gradually weakens. Self-healing concrete changes these rules. Thanks to bacteria or microcapsules, it can heal microdamage before it becomes a problem. That's why the service life of structures can nearly double, from 100 to 120 years. That means one bridge or building can stand for 2 human generations without major repairs. Sure, this material isn't cheap yet. It costs several times more than regular concrete, on average 3 to 5 times more. But if you look at the long game, it's totally worth it. Maintaining, repairing, and restoring structures costs governments and companies millions of dollars every year. Self-healing concrete cuts those costs to a minimum. Basically, it's like buying a car that changes its own oil and fixes its own brakes. Expensive upfront, but then smooth sailing and economical. The Netherlands became the real home of self-healing concrete. Right here, at Delft University of Technology, the idea emerged to add living bacteria to the mix that could repair concrete from the inside. The man behind this idea is Dutch microbiologist and engineer Hendrik Jonkers. Nature inspired him. He noticed that certain bacteria can survive in limestone rock and create mineral deposits, filling micro cracks in stone. That's when Jonkers asked himself, if nature can heal stone, why not make concrete that does the same? In the early 2000s, he started experiments with different bacterial strains, looking for ones that could withstand concrete's alkaline environment and stay viable for years. After numerous trials, the best candidates turned out to be Bacillus pseudofirmis and Bacillus conii, spores that can sleep for decades and activate only when moisture appears. Jonkers added them to concrete along with a food source, calcium lactate. The results were mind-blowing. When the concrete cracked, the bacteria woke up and produced calcium carbonate, which sealed the cracks like natural glue. Jonkers called his invention bioconcrete, and soon the whole world was talking about it. Later, Delft University launched a project to test bioconcrete under real-world conditions. In 2015, the Netherlands built the first lakeside structure using this material. Years later, it remained in excellent condition without any repairs. Now Jonkers' lab is working with construction companies and governments from other countries, perfecting the formula to make it cheaper and more accessible. The USA and UK bet on the mineral technology for self-healing concrete, which doesn't require living organisms, but works through special microcapsules with healing substances inside. These countries are actively investing in research on materials that can automatically restore minor damage without human involvement. The principle is pretty simple, but looks impressive. Capsules or microcapsules filled with special gel, epoxy resin, or sodium silicate are added to the concrete mix. When the concrete surface stays intact, the capsules preserve their contents without reacting with the environment. But as soon as a crack appears, the capsule ruptures and the liquid flows into the damaged zone. On contact with moisture or oxygen, the substance hardens, gluing the crack edges together and returning the structure's original strength. These systems are currently being tested in US Army labs and British research centres, including Cambridge University. In the UK, they're even building experimental road and bridge sections with this material to track how it behaves under rain, vibrations, and temperature swings. American experts went even further. They're experimenting with capsules that can activate multiple times. Inside these capsules are microgels that not only fill cracks, but also expand on contact with water, creating a hermetic barrier against corrosion. This is especially crucial for bridges and skyscrapers in coastal cities, where concrete constantly faces moisture and salts. Test results show that cracks up to a few hundredths of an inch wide can seal themselves in less than a week. And if the damage is larger, the process takes longer, but still happens without human involvement. Such technologies can significantly extend the service life of roads, tunnels, and even military structures, which is especially valuable under extreme loads.